Welcome to Kitchen Table Electronics Lesson 5.3 AC Circuits, Resistors and Capacitors. In Unit 5.2 we took a close look at capacitors, doing our very best to look at properties of the capacitor and ignore the resistor by choosing values in a strange and to be explained way. Well, this is the time to do some explaining now. We're going to look at circuits composed of arbitrary values of capacitor and resistor and over any frequency, and we're going to do this using complex analysis of the impedances, the derivations of which are explained in the accompanying advanced topic for Module 5. So let's begin with a high-pass filter. This is the differentiator that we looked at in the last lesson. So a capacitor connected between the source, the signal source, and the signal measurement point here, and a resistor to ground. The transfer function, in other words the relationship between V out to V in, is given by this equation here. This equation is derived by writing down the complex impedance of the capacitor, the resistor, which is just of course just a real resistance, and then solving for the real part of the ratio or the modulus of V0 over V in, once again derived in the advanced topics. And here's the result: omega RC over 1 plus omega RC all squared, square rooted. So what you see with this function, as omega RC goes to infinity, this 1 becomes negligible and it looks like omega RC squared square rooted, which is just omega RC, divided into omega RC, and that of course is 1. So at high frequencies the transfer function of this circuit is 1, and at very low frequencies it goes to 0. Omega as always equals 2 pi times the frequency in Hertz. Alright, let's do measurement on this circuit. So what we are going to do is keep our resistance at 10 kilo ohms, because we know that doesn't load up the AD9850, but we're going to choose different values of C here and record the response of the circuit to a wide range of frequencies. So to do that we're going to program our AD9850 using AD9850 scan and record.py, and we're going to program a starting frequency of 200 Hz, a finishing frequency of 20 kHz, and then a multiplier step of frequency of 1.1. This of course is the transfer function that we're interested in fitting to that data when it's recorded. We are changing that a little bit, and so omega RC is being written here as B times F, where F is the frequency, and B then incorporates the R and the C and the 2 pi. So we're rewriting this formula as BF over 1 plus BF squared all square rooted, then a scaling factor here A because we're not going from 0 to 1 volt, and then a C because there is some background from our peak amplitude detector. So here's the circuit. It looks formidable, but this is all the stuff you've had before. So we have our Arduino programming our AD9850. Here we have our true peak level detector that we've spent quite a lot of time building and understanding. The output of this goes to the Arduino A0 analog input, and the output of the AD9850 is applied to the circuit under test, which is then AC coupled into our peak level detector here. Alright, so I started with a 2.7 nanofarad capacitor. When you run the scan and record, it's going to ask you for the Arduino supply voltage so it can calculate voltages. So I entered my 4.91 volts, the starting and finishing frequencies, the step multiplier, and here's the wonderful thing about this: we are going to take a large number of data points, but we are going to let the computer do it for you. So this is the huge leap you've made compared with the normal in-house version of Physics 333, where you would be using cumbersome equipment with knobs on it and taking data points one at a time. Here you're letting your computer sweep through the whole range of frequencies, and your computer is going to analyze the data for you too. So once we've acquired the data, we then need to analyze it. I have adapted the curve fitting program that we looked at when we learnt Python programming, and you have a version loaded on the website called Highpass Fit, either .doc or .txt depending on the website. So you know the routine to cut and paste this from Notepad into idle, and then here is it has all the usual import of libraries and so on up here, but now I list the things that are particular to this particular analysis. I'm inputting 3 parameters A, B and C, which I'm inputting here as ASCII characters and then turning them into floats A, B, C. And this is the starting guess for A in this equation, B and C. Notice I've written square root here as np.square root. The reason is that if you go up to the import section of the program, I've imported the numerical Python package numpy, and I imported it as np. So np.square root extracts the square root method from the numpy package. It's also present in the math package, but there's no point importing another package because we've got numpy on board. So you see this is exactly the function we had. Let's just go back to the previous couple of slides where we have bf over 1 plus bf squared all square rooted, and that's what you see here, b times x all squared plus 1 and square rooted, and that divides into b times x, where x is the frequency, this scaling parameter a, and this constant background c. Then of course this is the magic Python function that does all the fitting and returns the fitting parameters and the covariances. And then what we do is, having gotten the best parameters a, b, c, d, we then put them into this function here and then plot a line. So this is a numpy function that generates a range of, in this case, 100 points over the full range of x, and then plots it using this function here, test function, and here you go, it plots that onto the on top of the experimental data. Okay, so there's our fit. So as always, when this program runs, it first of all shows you the raw data, and then you close the window and go on to fitting, and it's going to ask you for starting values of A, B, and C. You don't have to be too close. The parameter optimization is pretty nice, but it's good to get it in the ballpark. You can see that the scale of this is about ½ a volt, so that's the value I put in for A. For the background term, I put in ½ a volt also. B requires the use of your pocket calculator. B is 2 pi RC, so that's 2 pi times 10 to the 4th ohms, that was the 10 kilo ohm resistor, and 2.7 times 10 to the minus 9 farads. B is a number on the order of 10 to the minus 4. Now of course we're going to take the actual value of B from the optimized fit, and here it is, and so we will then use this to calculate C. You can see that C is B divided by 2 pi r. And so now let's take this B value here of about 1.2 times 10 to the minus 4, and then we divide it by 2 pi r, and we get 1.9 nanofarads. This is quite a bit less than 2.7 nanofarads. We'll discuss the tolerances and reliability of these results in a few slides' time. This is a little larger error than I would expect, but it's not outrageous. Okay, so we're going to use the same setup here. So this is the data I just showed you with the 2.7 nanofarad capacitor, and then we're going to put 2 of them in series, from which we expect to get about half the capacitance, and we do. Once again, very approximately. And then we're going to put 2 in parallel, and we expect to get, therefore, double the capacitance, or about 5.44 if you believe this value. And uh-oh, we have got nearly 10 nanofarads. The fit looks very nice. This value looks horrible. Now, in fact, I believe I made a mistake and picked up a larger capacitor than I thought I had, and then I reran this. But I've left this bad data in here because I'm going to do a bit of detective work, and in doing that detective work, explain to you how to analyze experiments for a fit like this. Okay, so if you remember, the output of the program was the fitting parameters listed here. This is the Python list that contained A, B, and C. And so this was the value of B that led to this nearly 10 nanofarads of capacitance. The covariance matrix is on the diagonal terms, the variance of each individual parameter. So the first diagonal here, corresponding to A, is the variance on A. The second entry in the second list here is the variance on B. I've circled it in red. And the third entry in the third list here is the variance on C. The other numbers are the covariance between one parameter and another, and they tell you how much the value of one parameter depends on the choice of the other. Okay, so we can therefore extract the variance on B. Here it is, 2.45 times 10 to the minus 10. The standard deviation is the square root of the variance. So here is the square root. So we can now say how well this figure of 5.927, how well this figure has been extracted by fitting the data. And so if we incorporate this 0.16 here, it results in about a 2.7% change in the mean value of B. So in other words, what this variance has told us is how good our fit is. So this is only one of several sources of error, but it's telling us right away that the fit is quite good, and it's extracted, it's certain about the value of B to within about 3%. Okay, where else could we have errors? Well, C is calculated from the ratio of B to R. So errors in B add to errors in R in percentage terms, because we're dividing one quantity by another. The resistor has a gold band on it, and this means plus or minus 5%. So the total then is plus or minus 7.7%, or about 8%. This then would say that our best value of capacitance is this 9.3 nanofarads, plus or minus something less than a nanofarad. Now, how should this be compared with the value we would expect by putting two capacitors in parallel? Well, we add the value of the capacitors, and so if each is known to within 10%, which is a standard tolerance for a mylar capacitor, then the sum is also known to within 10%. So in other words, for 2.7 nanofarads, two of them in parallel, we should get 5.4 nanofarads plus or minus a half nanofarad. So you can see this absolutely does not account for our discrepancy of nearly 4 nanofarads between what we measured here and between what we expect from adding these two values of capacitance together. Now in this case, this error was so gross that I simply didn't believe the value, and I went back and repeated it and actually did a few other capacitance values as well, and they were all good. So I just made a mistake. But I left this in deliberately to give you a little guided tour of error analysis and how much you can get away with goofing off and saying, oh well, this experiment wasn't very accurate. And then when you find that you have a discrepancy that's so large you know you did something wrong, you have to go back and repeat it. Now in the case of the capacitance values for the case of the single capacitor and the two capacitors in series, they are still out of bounds of an error analysis like this, but not by very much. Not as bad as this case of getting 9.3 instead of 5.4 nanofarads. Okay, so we've learnt a little bit about error analysis, and we've learnt how to use this covariance matrix to put a number on the goodness of the fit of a parameter. So now we are going to take a look at the low-pass filter. This is the integrator circuit where we have the resistor between input and output and the capacitor shorted to ground. So at low frequencies this is an open circuit and V out equals V in. At high frequencies this is a short circuit and V out equals 0. Here is the expression we get from the complex analysis done in the advanced topic for the ratio of the magnitudes of V0 to V in, V out to V in, and it's 1 over omega RC squared plus 1 all square rooted. Now you see as omega goes to 0, this goes to 1 over 1, which is 1, so V out equals V in as we expect. As omega goes to infinity, this quantity goes to 0. So I have set up another fitting program that you will find in your toolkit of text files to load into idle called lowpassfit.py, and it fits this function here as a over the square root of bx squared plus 1. So this is this quantity here where x is the frequency, so 2 pi rc is b, so bx all squared plus 1 plus c, this constant to take account of the offset from your peak amplitude detector. And then the equation proceeds exactly as before. 3 parameters to put in, a, b and c, and your starting and finishing frequencies, and off you go. So here is the result. Once again the program will plot up the data without a line through it and ask you if you want to continue, ask you for the input of fitting parameters, and I put in again 0.5 for A and C, and 1 times 10 to the minus 4 for B, and the program immediately found the best parameters, which are listed here. In this case I used a 10 nanofarad capacitor, so a 10 kilo ohm resistor and a 10 nanofarad capacitor. The capacitance is given by B over 2 pi R, and so putting in R as 10 kilo ohms, I end up with 11 nanofarads, and this is within 10% of 10 nanofarads, so it shows you that in general this process works pretty well. Okay, so that is our lab on RC circuits. We're going to introduce a new reactive component in the next lesson, which is the inductor, and we are going to talk about inductive reactance.